So last week we started talking about integration or anti-differentiation, and the idea there was that we were undoing the process of differentiation. So this is sort of the inverse to differentiation, and just to give you sort of an example, let's say that you were integrating 2t with respect to t. Remember that these little bookends, the integral sign and the dt, the differential, those are just telling us that we want the antiderivative with respect to t of this thing in the middle, which we call the integrand. So I want the antiderivative of 2t with respect to t, and the thing that I would take the derivative of with respect to t to get 2t would be t squared. Because if we take the derivative of t squared, we would get 2t, which is what we want. So the antiderivative here would be a t squared, and remember that the antiderivative is ambiguous up to a constant. So we'll always have this plus c whenever we write an antiderivative like this. So we talked last week about how to define this antiderivative and then also some rules that we have for some basic antiderivatives. I would advise you for this set of notes to just keep the section 4.1 notes in front of you, the one that has all of the rules for integration, because I'm going to be using those rules a lot. So if you haven't internalized those rules yet, then it would be a good idea to just have those in front of you. So today we're going to expand on our integration techniques. So remember that I told you last time that because this is the inverse process to differentiation, it inherits a lot of properties from differentiation. And today what we're going to see is sort of the inverse to the chain rule. So we know for differentiation that we have this nice chain rule that if you take the derivative of f of g of x, so that you have an outside function and an inside function, then the chain rule says that you should take the derivative of the outside function, leaving the inside function alone, and then multiply by the derivative of the inside function. So today we're going to see how to invert this process. So we're going to take the the antiderivative of this right-hand side. And here's the basic idea behind this. So I'm going to show you what the formula says for our strategy here. I don't expect that this formula will be super meaningful to you right away. What I expect is sort of that you'll need to see a few examples before you can internalize what's going on. So don't worry too much about the abstract formula for now, but I do want to sort of talk through it for a second so that you can see what the general idea is going to be. So what we know is that, let's say that we're trying to integrate this underlined expression. So notice that that's the expression that we have up here. So we know that if we take the antiderivative here, then we should be getting, if we want the antiderivative of this underlined expression, we should be getting this, f of g of x. So let's see how we can reason through that. Notice that here we have an inside function, which is g of x, and we also have its derivative sitting around on the outside, this g prime of x. So the idea here is to perform a u substitution. We're going to introduce a new variable, we'll call it u, and that u is just going to represent that inside function, g of x. And now I'm going to rewrite this first integral in terms of u. So g of x will just become a u, so that simplifies things a little bit. And this outside term, the g prime of x, well, because g prime of x is just the derivative of u, that's the same thing as du dx. So we can rewrite this initial integral in terms of u by just replacing g of x with u and g prime of x with du dx. But here I can think of these dx terms as canceling because I have one in the denominator and one in the numerator. Now this is sort of an abuse of the notation, so notice that du dx is not necessarily a fraction, but this manipulation will still get us to the right answer. So I can pretend that we can cancel out these dx's, and then I get the integral of f prime of u du. So notice that this last integral is not dependent on x at all. So now we're integrating with respect to u, this new variable. Just like up here at the top right, we weren't integrating with respect to x, we were integrating with respect to t, and we knew how to integrate that top expression with respect to t. We're doing the same thing here with our new variable u. But notice that here I have f prime of u and I want its antiderivative with respect to u. But that's nice and easy. If you want the antiderivative of f prime, it should just be f. So we'll end up getting f evaluated at u plus c if we want this antiderivative. And then if we wanted to turn this into an expression in terms of our original variable x, all that we need to do is replace u with its expression in terms of x, which was g of x. So this would be f evaluated at g of x plus c. And that's exactly the antiderivative that you would expect for this underlined expression, because we know that the antiderivative here should bring us back to the original expression that we took a derivative of, which was f of g of x. So this is sort of our process for undoing the chain rule. And I think as we do some examples, this will feel less complicated to you once you see this in action. This is sort of the abstract or formal justification for the rule that we're going to be using. But don't worry too much about this justification for now. I think as you start to see some hands-on examples, it'll make a little bit more sense. There are two different ways of writing this derivative that I'm going to use. So I'm going to put a little box around them for now. Ordinarily, we've been using this bottom one. So if y was equal to 3 times x to the fourth, then I would write that dy dx is equal to 12x cubed. And that's a true statement, so this is just the derivative of y with respect to x would end up being 12x cubed. However, you can think of multiplying this bottom line on both sides by dx, and if you do, then you would make it to this top line. Now, the top line doesn't have any sort of inherent meaning outside of an integral. We aren't going to be defining the differential in this course, so we don't normally write things in this top line way. However, the top line does become a little bit useful whenever you're using integrals, because in integrals you do see a dx by itself. So we'll see this dx a lot, and then it will become useful to have things written in the form of this top equation rather than the bottom one. And I'll show you an example of that in this first example. So just be aware that those are two different equivalent ways of writing the derivative of y with respect to x, and I'll show you why we might prefer the top one in this set of notes. So let's look at problem 1. In problem 1a, what I'm trying to do is this u substitution. And by the way, at the end of these notes, if you still need more examples, what I would recommend is just that you Google u substitution, because that's normally the phrase that we use for this section of notes. It's a pretty universal term. So in 1a, I want to be applying a u substitution. And remember that what we did up here was that we let u equal the inside function. So I'm looking at this here. U is supposed to represent the inside function, and then du would become that derivative of the inside function. So in this case, I see a nice inside function here, which is 2x cubed minus 3. And I also see the derivative of that sitting around on the outside. So notice that if you take the derivative of the first underlined term, then that derivative would be 6x squared. So that's a very good hint that that first expression should be your u. Because remember that what we're trying to do is sort of invert the chain rule, and therefore we're looking for g of x and its derivative. So we found g of x, the inside function here, and we found its derivative sitting around on the outside. So I'm going to let u equal that inside function, 2x cubed minus 3. And what that means is that du dx is equal to 6x squared. So if I plug these in for the expressions that we have up here, then the integral would become, well, for this first term, I would end up getting u to the 20th power. So I'm just replacing g of x with u. And I'm trying to convert this into an integral that only involves u, like we did up above. So instead of a 6x squared, I don't want to write that because it involves some x's, but I do see that 6x squared can be written as du dx. So I'm going to replace the 6x squared with a du dx, and then we still have that dx sitting around on the outside. So I've replaced my integrand with a u to the 20th times du dx. But again, like I did above, you can think of these dx terms as canceling, and then this would just become the integral of u to the 20th du. And now this is just the integral with respect to u of u to the 20th power. And for this, you can use the rules that we talked about last week. So we know that if you are integrating something to a power, then the power rule for integrals would say that you need to add 1 to that power and then divide by the new power. So you can check the 4.1 notes if you need a refresher on some of the integral rules. But this is what we'll get as the integral with respect to u here. And then to finish off this problem, we would need to substitute, instead of u, we would want to turn in an expression in terms of our original variable x. So I don't want this to be my final answer. I would want to replace u with its expression in terms of x, which is a 2x cubed minus 3. So as my final answer here, what I would put is, instead of u, I would put a 2x cubed minus 3, and then that was raised to the 21st power divided by 21 and plus a c. So this will become my final answer. Okay, so that's a u substitution. And I want to show you exactly the same problem worked one more time, but this time with the upper version of writing these differentials rather than the lower version, which is what I just used. So you can decide which one of these you want to use. Either one is fine. I'm mainly going to stick with the second method, which I'm about to show you, because I think it's a little more convenient whenever you're writing down the u substitution integral. So again, the strategy will be the same. I see an inside function and its derivative on the outside, so it's a good idea to let u equal that inside function, which is 2x cubed minus 3. Now the idea here is, instead of writing this in the fractional form, the du dx, I'm just going to take the differential on both sides. So I would get that du is equal to the derivative of this right side times a dx. So this would be a 6x squared dx. And notice that this equation, if you just divide both sides by dx, you would get this equation over here. So these are equivalent to each other, but this right side is a little bit more convenient because now whenever I want to replace these expressions with their equivalent expressions in terms of u, notice that I can take this original integral and I can look at this first expression, the first factor, and I can say, well, that's a u to the 20th power. So this would be the integral of u to the 20th power. The convenient thing in writing this all on one line rather than in the fractional notation is that now I can take this 6x squared dx, and I know that that whole thing can be replaced with a du. So that prevents us from having to do the cancellation step that we did over on the left. So for that reason, it's a little bit more convenient when you're dealing with integrals to write this in the differential notation rather than the derivative notation, but either one is fine. Either way, notice that you get to the integral of u to the 20th du. Now that this integral only involves the variable u, we can integrate with respect to u. We would get that we should increment the power by 1 and then divide by the new power. And then because we took an antiderivative, we'll still have a plus c. And then for our final answer, we again want to replace u with its original value in terms of x, which was a 2x cubed minus 3. So I replace the u with that. That's all being raised to the 21st power divided by 21 plus c. So we'll get the same answer either way. I'm mostly going to prefer using this right side notation. In other words, to just take the differential on both sides and then try to replace the dx in the integral with a du. So my goal in sort of abstract terms is I want to take this dx and replace it with a du so that I can get an integral that only involves u. And once I have an integral that only involves u, then I can easily integrate using the rules that we talked about last week. So that's sort of the general goal in U substitution. And we'll do several examples of these, so don't freak out too much about this initial setup. I think the main difficulty in U substitution is just sort of getting used to the process. So I don't expect you to be immediately comfortable with this, but I'm hoping that as we do another 10 examples or so, you'll start to see the